This is ScoreBooster educational tutorials that is aimed at providing solutions to JAMB, SSC, and APTEP exams. So we have brought chemistry to you today, and the topic we'll be discussing is going to be nuclear chemistry. This is going to be the first video under nuclear chemistry, and the presenter, as usual, is Latif. Because we are taking time to build the foundation in this chemistry, today we are going to the nuclear chemistry simply because of the importance that is attached to that topic. All the topics are important, but we need to understand the hazard and the uses of all the radioactive substances so as to know how to be kept safe in our various working places. It is expected that after this class, students should be able to explain, they understand what radioactivity is and what is instability in element, or let me say instability in elements. The concept of half-life will be discussed, uses and dangers of radioactive materials. So, as a matter of introduction, we have discussed before the structure of atom, where we made to realize that atom is made up of different particles. The electron that is revolving around the nucleus, then the nucleus itself that contains both the protons and the neutrons. Collectively, protons and the neutrons in the nucleus are called nucleon, and that is where the mass of the element is, because the electron is very, very small, in fact negligible, when discussing the mass of atom. Within the nucleus, inside the nucleus, that we have proton and neutron, there is, we should not forget that proton is positively charged and neutron is neutral. There is a force of attraction between the two of them, not like positive and negative, but there is a nuclear force that binds nucleons together. That force is very, very strong. And another force, that is a force of repulsion between two like charges. That's when we have two or more atoms, so that we have two or more nucleons. So the protons in the nucleus of the first atom will be repelled by the proton in the nucleus of the second atom. It is like that. So in effect, if we look at what we are seeing now, it is like there is going to be a counterbalance, opposing effect. A force is holding two atoms together, another one is repelling them from each other. Definitely, if one overpowers the other, then something must happen. That is the basis of instability, and this instability is caused by when the electromagnetic force is more than the nuclear force. When can that happen? That happens when we have many nucleons, such that the nuclear force between each of the nucleons is not as strong as the force of repulsion between the pool of protons. Let's assume that we have like 90 protons now together. So the repulsive force between the protons will now be much more than the attractive force between each of the nucleons. That is what is called instability. And that instability, what will it cause? It causes release of energy and possible break of atoms. When there is break of atom and release of energy, the energy that is released is called radiation, and those elements are called radioactive substances. In discovering what is called radioactivity, the idea was first brought by a French scientist in 1896. That man was called Becquerel. He was working on phosphorescent material. What he did was that he placed some uranium crystals on black paper, and he used he covered the uranium with a thin film, and that film was covered with a black paper. What I'm saying is this: there was a uranium crystal. He put it inside the paper, then he put everything, like when he's trying to keep something, he put everything inside the film. After some times, he noticed that on that film outside there were patches. Then he did the same thing for other elements. He noticed that there was no patch. Then what could cause it? Unknowing to him that time, he knew that something was responsible, but he did not know exactly what happened. So later, a Polish scientist called Marie Curie, she was a woman, and herself with her husband, they worked tirelessly on radioactivity, and in 1803 they were awarded Nobel Prize of Physics. The three of them, the Henry, the Marie, and Pierre, the three of them were awarded Nobel Prize in Physics for their contributions. So in furtherance to their work, Marie and her husband discovered two other elements. The name is polonium. Polonium is in honor of the country where that woman came from. Marie Curie, that came from Poland, so they use polonium. And the other element is radium. Radium is from radiation, because radium is a very highly radioactive, so they named that element radium. So after about 7 years, in 1911, Marie also received a Nobel Prize in Chemistry. So that makes her one of the few scientists to have been awarded 2 Nobel Prizes in Science. So for detail of her life after discovery of radioactivity, I put a slide at the back of this video. It is called radioactive decay. Radioactive decay is just when we have unstable nucleus releasing energy to form another substance. We have understood what is called instability. So during instability, elements form another substance. That is what is called decay. When it forms another substance, it has decayed. It decayed from another substance. So the radiation that are released are of 3 types: the alpha particles, the beta, and the gamma rays. Schematically, this tells us the strength in terms of penetration power of each of them. We are going to examine each of them one after the other now. Let's start from alpha particles. An alpha particle is made up of 2 protons and 2 neutrons bind together. There's no electrons, so it makes it a positive charge. And we have 2 positive charge and 1 other neutral charge. So it means that in the nucleus we have 4 mass units. So it makes it a very dense particles. And making it a dense particle means we expect it to have a very low penetration power. What is called penetration? Penetration power is just the measure of how deep a substance can penetrate in another substance. As low as the penetration power is, even a piece of paper can stop it from penetrating. It cannot pass through a piece of paper as thin as a piece of paper is. This is because it is too big to pass through. Then alpha decay occurs because the nucleus has too many protons. We should not forget what we discussed about instability. When we have too many protons, there's going to be force of repulsion. So electromagnetic force that is between the repulsive forces between the protons will now be more than nuclear force that is binding the nucleons together. So that will now make the atom to break. Then there is decay. This decay will now release alpha particles. This can be shown by the decay of americium to neptunium, this equation. These alpha particles, here we use helium because it's helium that is having 2 proton and 4 mass number. So you can write helium here. If you put helium here, 4 2. So if we had 4 plus 2, 34, we get 241. If we had 2 proton, 2 electrons, plus 93, so we have 95. So it depends on representation. One can use this sign, one can use the normal sign of helium. The most important thing is to make it balanced. Beta particles is just when we have too many neutrons. There's going to be a conversion of that element with too many neutrons. Convert it to a proton, electron, and another particle. Neutrino. A neutrino is other particle that is released from the sun, and very, very small, and the effect is very, very small. So because if the effect were to be big, everybody will have had skin burn, but it's very, very small, and it costs billions of it to have effect on the human body. The energy electrons that are released in this way are called beta particles. They have higher penetration power than alpha particles, and they are able to pass through some materials like paper, but aluminium can stop it from passing. During beta decay, the number of atoms decreases by 1. We should not forget that we said it's going to release a proton, electron, and another particle. So if we look at this equation now, this is an element that has many protons, as we can see now. Here is having mass number that is 3. Proton is 1. So that means neutron is 2. So neutron is far more than a proton. So we can say it has too many neutrons. So when this thing now breaks, when it decays, we have a proton like alpha particle, we have a beta particle here, then we have the other particle that is it's very small, neutrino. If we look at it now, this one has become 2, 3 remains unchanged. What happens? That means there is another particle here that has no mass, and the electron is negative here. That is why if you add -1 plus 2 here, you get 1. If you add 3 plus 0 here, you get. So it depends on the way we want to represent it. We can represent it using this symbol, or we represent it like electron. We put 0 on top and -1. We will see it when we are solving examples by the grace of God. A gamma ray is just the collision between particles in the nucleus. When they collide, there is going to be release of energy. The energy that is released is called gamma ray. Gamma ray is having a very high frequency and very high penetration power, no mass and no charge, so it can pass through many substances because it is very light, no mass, no charge. It can pass and nothing can stop it. Even in magnetic field, nothing can stop it because it is carrying no charge. It can pass through common substances. Even including metals, only lead and concrete can stop it from passing. On visible light, it is above the visible, on the spectrum, rather electromagnetic spectrum, it is above the visible light simply because of its high frequency. They'll talk about that more in physics. Gamma decay occurs if the nucleus is at too high energy level. Since gamma rays are part of electromagnetic spectrum, they can be thought of as waves or particles. Yes, that is what we just explained. When we talk about atomic physics, they will talk more about this sentence. Atomic number during a gamma decay, atomic number of the element and atomic mass, both of them remain unchanged because the gamma ray is having no charge and no mass. We should not forget that in alpha particle, we say that the mass number reduces by 4, the atomic number reduces by 2. In beta decay, mass number does not change, atomic number increases by 1. But in gamma decay, nothing changes, mass remains unchanged, atomic number remains unchanged, simply because gamma ray has no charge, no mass. This is just a simple table that shows the comparison of the three of them. Alpha particle is having 2 proton and neutron. Change in element, yes. Neutration power, low. Beta particle, is there change in element? Yes, because there is increase in number of proton. Another element has formed. Neutration power is maximum, medium. That is, if you compare it between alpha particle and gamma ray, it falls in the middle. In this gamma, is there change in element? No, because no mass, no atomic number change. Implantation power is very high. What are the sources of radiation? We said radiation are very dangerous in some cases if carefully handled. There are some places that one can be exposed to radiation. It can be by natural source or man-made source. The natural source can include the cosmic radiation from the earth, from the sun. When we have release of energy from the sun, now interact with particles in the atmosphere and magnetic field, so it can cause some cosmic radiation. But thank God, those are not as dangerous as we have it in man-made radiation. Terrestrial radiation is when we have a naturally occurring element that is radioactive. So if something now comes close to it, the body can be exposed to that radiation. Man-made sources could be from medical examinations, could be from smoking, could be from watching televisions, because television we have electromagnetic rays, from building materials. Those are man-made sources. Another concept that we are going to talk about is half-life. The half-life has various definitions, but the fact is, no matter how the sentence definition is being constructed, the half-life is time it takes for half of that element to decay. If the element is, example, let's say initially we have 8 grams, like we have put it here. From this table now, sodium 24 is this one. Half-life is 15 hours. It means after 15 hours, the half of 8 will have decayed, so 4 will have gone. After another 15 hours, 2 will have gone, remaining 2. After another 15 hours, 1 will have gone, remaining 1. After another 15 hours, like that. That is how it will be going. That is what is called half-life. Even if we start with 50 grams, after the half-life, after that time of that element, half will have gone. After the other time again, half will have gone. That is what is called half-life. Half-life. We are going to do some one example here, and we are going to solve some problems in half-life. What we just need to know is that we are not to cram these values. This is just example. There are many elements that are radioactive, not only this one, so there is no need of cramming this. So example, let us solve this example now. 100 grams of cesium-137 is allowed to decay. Calculate the mass of cesium-137 that will be left after 90 days. So if we look at this problem now, we don't know the half-life. we need the half-life to know what will be the mass after 90 days. So looking at this table, this is H137, the half-life is 30 years. So the half-life of sodium is 30 years, I've put here. So after 30 years, this is just a step-by-step approach. After 30 years, half will have gone, remaining half, 50 grams, will have gone, remaining 50. After another 30 years, making 60. The mass left is going to be half of that 50. After another 30 years, making 90. The half remaining is this. This is just a step-by-step approach to just illustrate what we are seeing. But in the JAMB exam, there is no luxury of time to be doing this. Instead of that, what we did is this. This half is constant because it is half that we're talking about. This is half. So here on top here we have x ordinarily. We have x. This x is the number of time that the quantity is halved. Here is the starting mass. In this case, it's 100 grams. So if we look at it now, 30 years is the half-life, and we are going to 90 years. So how many 30 can we get in 90? 3 times. That is why I'm putting 3 here. If you multiply this, you get this, which is the same answer as the one we have done before. So just look at this example and solve this class exercise. So after seeing this question, pause the video, look back to that example, study it carefully, and compare your answer with what I've got in here. Oh, I want to believe that you have done that. So to check if you really get the approach, this is my own solution. Although in JAMB you are not meant to write all these stories, this is just for illustration's sake, so that somebody will know how everything is obtained. We said before that radiations are very dangerous and at the same time are very useful. These are some of the dangers of radiations: skin cancer, blood cancer, and every other cancers can be as a result of too much exposure to radiation. We can have genetic abnormality where the chromosome is destroyed and transformed to another thing. Damage to the cells. Cells are damaged prematurely. This is as a result of exposure to too much radiation. So let's talk about uses. The use of radiation are very many. Number one, in medical field, they use it to detect if any organ is not functioning well, like a broken bone, a dislocated joint, something like that. Human eye cannot look into the body of man, so that is why they use radiation. They expose it to radiation and the ray will enter. We should not forget that there are some things that can stop the ray from passing. So the bones will stop it. Every other thing, the ray will pass, then the bones will stop it. So where the bones, anywhere the bones stop that radiation, the image will be brought out clearly. So the doctors will see and make necessary medical corrections. It is also used to sterilize medical instruments. Radioisotopes are used to analyze pollutants, that is environmental science. Archaeological studies are used if you want to detect the age of a particular organic remain. Let's assume that historically they tell us that something happened 400 years ago, 300 years ago. How do they know? It is an application of radiation. It is also applied in food preservation, genetics, and biochemistry. There are many uses of radiation, and it is my aim that after reading this, students will be able to get more and be acquainted with it, because it is something that is connected to Earth, safety and environment. This is where we are going to stop for today. For those that are interested in the story of Marie Curie, so I have put this slide after this so as we appreciate the work she has done for us in physics and chemistry. Our next video will be on artificial transmutation, where we talk about nuclear fusion, nuclear fission, differences between nuclear reaction and chemical reactions. We are going to solve some problems and provide some solutions. Thank you very much for listening. Have a wonderful day, and don't forget to share our video, like it and subscribe to our channel. Thank you.